This is section 11.6, part 2. In this case, we would like to again find the equation for a tangent line to a graph. In this case, the graph is cosine t, sine t, 3t. So we're looking for the tangent line to a three-dimensional graph this time. This is something we would not be able to do using our Calc 1 techniques, just y equals mx plus b, since everything is now three-dimensional instead of two-dimensional. Fortunately, with vector functions, it's really easy to go from 2 to 3 dimensions, right? All we have to do is add a z component. So we're going to work this problem just like the problem that we just finished. We're going to say that we need a direction vector and a starting point. The direction vector, the tangent vector, is always our derivative, which in this case would be negative sine t, cosine t, 3. And we're doing this at the point where t equals 0. So I'd have negative sine 0, cosine 0, 3, or 0, 1, 3. So there's my direction vector for the line I want. I also need a starting point. And in this case, we happen to have been given t equals 0 as the point of tangency. So we'll go ahead and do r of 0. Again, just a reminder, we always use whatever the tangent point was. It happens to be 0 this time, but if it's a different t value, we don't put 0 in here. We put the point of tangency. So only 0 because that was the point of tangency in this case. So r of 0 would be cosine 0, sine 0, and 3 times 0, or 1, 0, 0. All right, that means the equation of the tangent line, which I'm going to call L of t times my direction vector, plus the vector we got from the starting point, or 1, comma t, comma 3t. All right, the other part of this problem said that we should sketch the graph and the tangent line. I won't be super specific here, but just to give us an idea of what this would look like. Remember that this is a helix, right? This would be a circle of radius 1, and it's stretched in the direction of the positive z-axis. So, this is a helix. And we actually already know r of 0, our starting point, is 1, 0, 0. So right here. And as we go around our circle, we also stretch up that positive z-axis. So this is r of t. This tangent line would be the line that's exactly tangent at that starting point 0 and in the same direction. So it would go this way just because the curve itself is moving this way. Okay? So that would be my tangent line L. In the Maple investigation that you'll be doing for this particular, that goes with this particular section, I'll actually be asking you to do some graphing of curves and tangent lines. And it's going to be this process that you'll use. We just did it by hand, you'll do it on Maple. But you'll graph the curve using Maple, you'll also graph the tangent line using Maple, and you should be able to actually see that tangency really well. All right. A couple of other things to do with tangent vectors, which we now know are just derivatives. In example 6, instead of a tangent line, I'm just asked to find a unit tangent vector. to the graph of this r of t at the point where t equals 2. This is a more complicated r. I'm not going to try and draw it, although we could with Maple. But we can certainly find the tangent vector. We know that the tangent vector is always the derivative. So let's see, our derivative here would be 2t, comma 2, comma negative 3t squared. And this particular time we want to know the vector tangent at the point when t equals 2. So if I plug in 2, I'm going to get 4, 2, and negative 3 times 4, or negative 12. Okay. I'm almost there. I have a tangent vector, but the problem asked me for a unit tangent vector, so my unit tangent, of course, I can get just by taking the tangent vector and dividing it by its magnitude. What do we got there? 144 and 20 would be 164, which would be 4 times 41, so 2 square root 41 on the bottom. And that means I can simplify just a little bit. I'm going to write my final answer as 2 over the square root of 41, 1 over the square root of 41, and negative 6 over the square root of 41. So that's all there is to that one. I wasn't asked for a tangent line this time, just a unit tangent vector. All right, example 7 actually should, I hope, take you back to your days of high school geometry just a little bit. The property that's described here is one that's told to every high school geometry student, but the reason why it's true isn't usually explained, because using just geometry, it's hard to explain why this works. Using vector calculus, it's going to turn out to be really easy. So here it is. We're going to show that the tangent line to a circle is always perpendicular to the radius of the circle at the point of tangency. If I sketch this, and I'm actually going to put it on some axes, let's just pick a point of tangency, let's say right here. The tangent line to the circle would look like that. And we're supposed to show that it's perpendicular to the radius of the circle, which I'm going to actually draw as a vector. So let's see here. If I consider this to be the vector r, and I'm actually going to go ahead and say, if I go ahead and parameterize that circle going counterclockwise, then r is just going to be, I'm going to say this is a circle of radius a, be a cosine t and a sine t. Right? So that's your radius vector. It's just a vector with its point on the circle. Typical parameterization for a circle. All right, I'm going to next say this whole line will be perpendicular to r if just the tangent vector is perpendicular to r. So let's go ahead and concentrate just on the actual tangent vector. Maybe I'll call this, oh gosh, I want to be careful not to use something that I don't want to use. Let me just call this v tan. That's fine. That's what we've been doing, right? The tangent vector would be r prime, and that's the derivative here, which would be negative a sine t. a cosine t. And our goal is to show that those two are perpendicular, right? That the tangent is perpendicular to the radius. Well, what do we know about perpendicular vectors? We know that their dot product is 0, right? So if I check the dot product of these two vectors and get 0, I will know that those are perpendicular. So let's do our dot product with the tangent vector. And I'm going to get a negative a squared sine t cos t plus a positive a squared sine t cos t, which of course does give me 0, meaning that r is perpendicular to v tangent. So we got exactly what we wanted there. We showed pretty easily, using vector calculus, that the radius and the tangent vectors are perpendicular. All right, so at the bottom of this page is just a real quick little summary of using the derivative as the tangent vector. Right? If we've got a curve, 2 or 3 space, doesn't matter, but the curve defined as a vector valued function, then the derivative, r prime at a particular point t naught, is going to be a vector tangent to the graph at that point. That derivative vector can be used as the direction vector for the tangent line. And then the one example we did at the top of this page, the unit tangent vector can be found by taking the derivative vector divided by its own magnitude. This is a little notation that I didn't actually use when I did the problem, but I'll introduce it right now. Instead of u subtangent like I did it up here, we typically use the notation capital T to represent the unit tangent vector. And so anytime you see capital T, always think of that as not just the tangent, but the unit tangent, derivative divided by its own magnitude. All right, we will go on and look a bit at integrals of vector valued functions in our next video.